Okay, switch on laser pointer. Okay, so what I wanted to do was I wanted to tell you what emergence really means, and I wanted to connect that with the other side of emergence, which is what I think of as minimal models, because I think the concept of emergence is very poorly understood, and I want to make it crystal clear to you right at the beginning why it's an important concept and what one can do with it. So let me start off by talking about the hardest example of emergence. The most interesting examples are complex systems and biological systems. So the things that I'm interested in from a research perspective are systems which have strong fluctuations, unpredictable and nonlinear dynamics, multiple scales of space and time, emergent structure, which I'm going to say what that means, and active components. So these are all the types of phenomena that are really the most challenging in physics. In this class, we won't be able to understand all of these things. It's not a class on complex systems, but we will understand some of the basic principles for dealing with these systems in very simple physical formats. And the other thing I didn't mention was nested feedback loops, which is part of the way the things that differentiate biological systems from physical systems. Okay, so so you can see I'm not used to doing this. So let me switch on my clock here. I didn't set this up. So I'll just keep an eye on the time. Okay, so complex. So why am I interested in complex systems? Well, if you think about it, when you think. Okay, so another thing I should do: silence my phone. Okay, so the idea is this: that if you're looking at a complex phenomena, they're usually the hardest ones to deal with because of all these multiple layers of interactions between different phenomena, and so it's the things that you're taught about up to now in physics are sort of ones where reductionism has been the main way that you make progress. Classical mechanics as being the example of that. Few body physics, you just calculate Newton's equations and so on. But the things that we're going to be interested in this class are where the interactions between the degrees of freedom are so strong that you get qualitatively new features. And if that sounds a lot like phase transitions, you're right. It is part of the sort of phase transition phenomenology, but it's more than just that. So I would say the following: most of what you've learned up to now has been systems that are weakly interacting, degrees of freedom that hardly interact at all, and if they do interact, they act weakly enough that you can use perturbation theory to understand it. What we're really interested in systems where the interactions are so strong that you get new features coming out, and I'll say exactly what I mean by that in a few minutes. And we tend to call those things emergent phenomena. And understanding emergent phenomena is a necessary but not sufficient condition for understanding genuinely complex systems. Okay, so that's the sort of propaganda. Now, this field, I would say, grew out of condensed matter physics, and the preeminent condensed matter physicist of the last 40 years or so was probably Phil Anderson, one of several competitors for that title. Phil Anderson was incredibly influential. He passed away relatively recently. Did a lot of work in basic solid state physics and some of the things that we're going to be talking about in this course. In 1972, he wrote an incredibly influential commentary in Science called More is Different. And what he was really trying to say there was that as you start adding more and more degrees of freedom, you start getting different phenomena coming out. And he related this to the hierarchical structure of theory. He related it to complexity. He tried to make the point that just because you have more degrees of freedom, it doesn't mean that things just get more complicated. They also get more complex, and you get new things coming out. And so that's really where every serious discussion of emergence needs to begin. So I want to do an experiment. Now this experiment is quite fun one to do in an actual class or an actual lecture. Harder to do when we're all sitting in an individual room. But so everybody needs to participate in this experiment. So the experiment is very simple. What you're going to do is you're going to take your finger. So everybody who's got their video on, I can see about half a dozen of you, and you're going to poke it up at the ceiling like that, just like I just did, okay? Okay, everybody do that? Did anybody find that their ceiling moved up or cracked or broke or anything calamitous like that? Anybody see that? No, I can see somebody shaking their head. Nope, it didn't happen for me either. Okay, so that didn't do anything. Now, what I usually do when I do this live is I then get a chair. I stand next to the chair. I put my finger on the chair. I don't really have a chair. Do I have something that can be a proxy for a chair? Not really. Well, maybe. You know, here's a water bottle, which I can hang up like this, and I can. Yeah, this isn't going to work with the screen. I can poke this water bottle, and it will fall over. Okay, so let's just do that again, just so that you can see it. Here's a bottle. So I push it over, and it falls. Now this is a kind of, you might say, well, what the heck is so interesting about that? Why is it that when I push something, it moves, but when I push the air, it doesn't move? And so the interesting thing about this, and why this experiment is so interesting, is that in one case you have a solid where you have atoms that are sitting around and they're in a solid. In the other case you have atoms and they're a gas in a room or maybe a liquid. But one of them you can push and the other one you can't. One of them you can transmit a force and the other one you can't. And you might say, well, we know why that is. It's because one is a solid and one is a liquid. So let's think about whether that's really true. Here's a kind of cartoon picture of the experiment that we did. We have atoms in a box, they're bouncing around. And of course, the thing that differentiates a liquid or gas from, say, the solid, which was like the plastic bottle that I pushed, was that at low temperatures it forms a crystal. And the crystal is something that's very different from a gas. Why is it different? Well, if I look at the atoms, they're in some periodic array. If I look at the atoms in my plastic bottle, they're not in a periodic array. The plastic bottle is amorphous, but the atoms are fixed in specific locations. So what you have in the solid is you have atoms that have special locations, and in the liquids they're floating around. And so you might say, well, that's the difference between a solid and a liquid. Okay, so if you wanted to measure that difference, how would you do it? Well, if you have a crystal, what you learned on your mother's knee is that what you do is you shine X-rays at the system and you look for Bragg scattering. If you look for X-ray diffraction. Of course, if you have a disordered material like my plastic, the plastic in my bottle that I just pushed over, there you don't have a periodic order, so you won't get any Bragg peaks. But then you say, well, of course I can tell if it's solid. The way I can really tell that is by measuring its shear rigidity. If I take a gas or a fluid and I try to shear it, I can't shear it. Well, I can shear it at high frequency, but I can't shear it at low frequency. Whereas if I have a solid, if I try to shear it, it will fight back. It will exert a restoring force. And so the response of the system to this shear perturbation is different for a solid than it is for a liquid. So what I've just told you then is that the thing that differentiates a liquid or a gas or a fluid from a solid is not necessarily that you form a crystalline order, because you can have a solid without crystalline order, but that the way it responds to a perturbation is different. One responds where you can shear it quite easily at any frequency you like, and the other, if you try to shear it at a low frequency, it doesn't like to be sheared, and that's what defines a solid. So if you really wanted to measure the level of solid order, what you would measure is the static shear rigidity of the material. Okay, so why is this interesting? Well, the thing that's interesting about it is this: the underlying physics of the crystal or the solid state is exactly the same as the fluid. If I wrote down the Hamiltonian for the system, the Hamiltonian is just the total energy, so it's just the kinetic energy plus the potential energy. Both the fluid and the crystal have exactly the same Hamiltonian. So when you lower the temperature, you haven't actually changed the interactions between the atoms. They're still obeying the same Hamiltonian, but yet the behavior of the system, the way it responds, has now become completely different. So what we've learned then is that the pairwise interactions between atoms did not change, but the correlations between them did change when the temperature was lower. When they were in a fluid, they were just flying around at random. When they were in the solid state, they were at some fixed positions, and they also exerted a restoring force when you tried to shear them. So in some sense then, the solid state emerged as if by magic out of the fluid state. You have exactly the same physics, but as you lower the temperature, something different happened, even though you didn't change the basic interactions between the constituents. So in some sense, the big deal about emergence is that the solid state has its own new laws of physics. Okay, so I start off with atoms, and then I cool it down, and now I get a state that has its own new laws of physics. And here's, you can see what those new laws are. What's happened is the atoms formed a crystal, as shown here, and they're connected by springs. And these springs are what gives rise to the rigidity and the elasticity of the solid. The thing about it is that we didn't put those springs in by hand. Okay, so if you look at a solid state physics textbook, Ashcroft and Mermin or whatever you've used in the past, you'll start off by saying, here's the Hamiltonian for a solid, and it will be a bunch of particles connected by springs. Those springs don't exist. Those springs are really just the original Hamiltonian that you had for the fluid. But when you go lower the temperature, the springs emerge. The emergent phenomena here is the existence of the springs, and that gives you new long-range forces in this material that are completely different from the original forces between the atoms. And that gives rise to the phenomenon of elasticity. And by elasticity, what we mean is the response of a solid to external perturbations. And it's completely different for the solid than it is for the fluid because of the emergent springs. So there aren't real springs here, they are emergent. When you write down as a model of a solid, say to describe phonons, you put these things in by hand. But but if you really wanted to do it from first principles, you should start off with a Hamiltonian for a bunch of particles bouncing around in a box, and you should be able to derive the existence of these springs. And you should be able to calculate the shear rigidity and elasticity as you go through some kind of phase transition that separates the fluid state from the solid state. So where do these new laws come from? The new laws that describe the solid, they are collective, because all of these atoms now are now connected by springs to all the other atoms. So this is a collective phenomenon, and in fact, the elasticity is a property of the statistical mechanics of the atoms. So let me give you an example of that you may know, which is, do I have an example of it over here? I don't. Let me just quickly look. Do I have an elastic? Nope. No elastic band. All right, elastic bands. Okay, you take a rubber band and you pull it, and you can stretch it really well. Okay, so where do the restoring forces come from that make an elastic band so elastic? Well, what you have in it are polymer chains. And those polymer chains get cross-linked together by usually sulfur bridges that provide, if you like, chemical staples between the polymer chains that make up a piece of rubber, an elastic band, a rubber band. But the reason that it's a solid and the reason that it's stretchy is not because the polymers themselves are solid. In fact, each individual polymer is flapping around in thermal equilibrium like this. You can make a solid built out of bricks by stacking them one on top of each other and making a brick wall. And you've built a solid by putting together other solid materials. Or you can make a solid by taking something that is floppy, like a polymer chain, and cross-linking them together. And even though each individual ingredient is floppy, because of the way that they interact with each other, because of the way that they get in the way of each other and reduce their entropy, because of the way that they're topologically entangled, the resulting material is solid, even though the individual ingredients are not. So the solidness of a piece of rubber is something that has emerged from the collective statistical behavior of the underlying level of description, the polymer chains. So when we say that emergence leads to new laws of physics, and I say the solid state has its own new laws of physics, are they really new laws of physics? And I would say absolutely they are, because at the level of description of a solid, the actual interactions between the atoms cannot be detected. Only the continuum mechanics of the solid is observable. So you take a material, iron or steel or a rubber band or whatever it might be, and you can't even tell that it's made out of atoms. You wouldn't know that. You just think it's just some continuum stuff which behaves in some way that was first described by people like Cauchy and others in the 19th century in terms of elasticity theory, long before they had any idea that these things arose as emergent properties of the interactions of smaller degrees of freedom than the atoms that make up the material. And so at the level of a description of a solid, that's all you have. You just have the solid, and you've now lost the memory of what happens on smaller scales, and all you can see is the continuum mechanics of the solid. So they really are new laws of physics at that level of description. And in fact, I'm going to show you in a minute, whenever you talk about the laws of physics, you have to talk about what level of description you're talking about. And in some sense, all laws of physics are emergent. So I'm going to get to that in just a minute. So what I just told you is it took so long for the existence of atoms to be deduced because this emergent phenomena is so effective. Once you have this macroscopic continuum behavior that arises from the interactions of atoms, you can no longer see the existence of the atoms that gave rise to it. So where do the atoms and their interactions actually come into this at all? I mean, do we really care that atoms exist? Well, we do, because let's suppose you wanted to know, well, what is actually the Young's modulus of this piece of metal? Or what is the static shear modulus of a piece of rubber or something? Well, in the way that we describe these laws of physics, these are just phenomenological parameters. And if you have a level of description that is a lower level, then you can compute these things. So let me give you an example of this. When you do atomic physics or you do chemistry, you know that you have, say, the mass of a hydrogen atom, you have the mass of a proton, you have the mass of an electron, the charge, and so on. And those are your basic ingredients. And as you do chemistry or atomic physics, you just now solve Schrodinger's equation for all of these things, and you try to include as your basic entities just electrons, protons, neutrons, or atoms, or something like this. And you have in there, what is their mass, what is their charge, and so on. These are phenomenological parameters. You don't know where they come from, they're just things that are measured. But then on the other hand, if you go down a lower level of description, now you go down to QCD, or you go down to the electroweak theory, or you go down even further, say to the to string theory or grand unified theory, then in principle you ought to be able to compute those things. So what I'm telling you is something that those of you who've taken my StatMech class already know, is that we focus in physics on different levels of description. And those levels of description at the higher levels emerge from the lower levels. And once you're at those higher levels, you don't really see what's happening at the lower levels. So as an example, when you're doing atomic physics or chemistry, you never need to know, what is the mass of the top quark, or what are its radiative corrections and things like that. Those things all just bundle together into some one parameter, which is just the mass of a proton, or the mass of a neutron, or something like that. So somehow this is connected to the normalization, that all the physics on smaller scales are somehow bundled in to one or two phenomenological parameters that describe the impact of those lower scales on what is at the higher scale, the longer scale that you're actually interested in. Now, one of the things that I want to emphasize, and we're going to be talking about this in this class, is that emergence always leads to what I'll call generalized rigidity. So when we're talking about solids and liquids, we understand what we mean by rigidity. We literally understand it in the sort of colloquial sense of the word. But when we're talking about more complicated physical systems, ones with strongly interacting condensed matter, exotic states of matter, and so on, when we look at emergence, what we're looking at are response functions. We're looking at how systems respond to perturbations, and they have some analog of rigidity, which I will call generalized rigidity. And we're going to see that this concept is the thing that gives coherence to the idea of emergence, and it's how you measure things. In biological systems, this rigidity has another name. It's sometimes called resilience. So just fantasizing for a moment, let's suppose we had an understanding of how it is that I can have a bunch of people, or a bunch of insects, or social insects, or a bunch of bacteria, and they all exhibit collective phenomena. They flock, they swarm, they vote the same way as their friends, whatever it may be, things like this. They have some kind of collective behavior. That collective behavior should be quantified by being able to say, well, what is it that holds them together? What is it that keeps a flock together? How does it stay together? How is it that when you try to perturb the flock, the birds or the bees or whatever there are swarm together and don't all just fly off in different directions? And you can make models in the way that we are going to be doing in this course to try to describe these things. And this, in fact, is something that I'm actively interested in my research group, trying to understand the cohesiveness, the surface tension of flocks, the collective behavior of social living systems. Okay, so what I've told you then is that emergent levels of description absorb the properties of lower levels of description into phenomenological parameters, typically a small number. This is one of the things that makes fundamental physics hard. So I tend to differentiate what I do as a statistical physicist, a condensed matter physicist, or sometimes a biological physicist, as being opposed to what other physicists say who call themselves high energy physics physicists or elementary particle physicists do. And that is because what we're trying to do is take a level of description of matter and then ask what are the consequences and what of their interactions and what are the new laws that emerge at a higher level. So we're trying to understand the behavior of electrons in a magnetic field in 2 dimensions, for example, and we find that there's many new exotic states of matter that emerge from that. But we know that the lowest level of description that we're thinking about is just electrons and a gauge field. When you're trying to understand fundamental physics, what you want to know is what are the laws of physics at a lower length scale. So you want to start off with your material, which you can describe by elasticity theory, and then try to deduce the existence of atoms. That's one way of going down to lower levels of description. Well, once you've gone down to atoms, you want to go further still. So you want to look inside the atom, you can see a nucleus, you can see electrons, and then you want to go inside the nucleus, you see neutrons and protons, you want to know what they're made of, and so you want to go further and further down in length scale, smaller time scales, and the higher energy scales. But because the flow of emergence is to larger scales and larger time scales and lower energies, then when you're trying to do fundamental physics, you're kind of going the wrong way. And the reason for that is something that we'll talk about a little bit later, which is universality. And what universality means is that different descriptions microscopic descriptions can have the same description at a macroscopic level. So the mapping of going from one level of description to a higher level of description is many to one. And that means that if I start off at the macroscopic level and try to find out what are the laws of physics on smaller scales, it's a mapping that goes from one to many. So there's many microscopic laws of physics that are consistent with what you see at a large scale. So currently, right now, you have to spend billions of dollars and do an experiment under the Swiss Alps in order to measure something that we can't explain by our existing description of the standard model. But we know very well that that description is an effective description, and if we could do much higher energy experiments, we would find we would see many different phenomena that could be there. For example, supersymmetry or something like that. So we have many candidate models for what may be there at higher energies and smaller scales, but we don't know which ones are the right ones because all of those different models would have the same behavior at the large scale. And so that's why fundamental physics is hard, because one is going against the flow of emergence. And so what that says is the idea of reductionism is kind of doomed right at the outset. You're never going to be able to find the ultimate, the ultimate level of description. But if such a thing even exists, which I doubt. But anyway, the collective properties of matter can be understood and should be understood without requiring knowledge of all the way down of the different levels of description, and that's kind of what this course is about. So we have to ask only the right questions. Okay, so one of the other characteristics of uniqueness that I want to talk about, characteristics of emergence that I want to talk about, is that it is associated with loss of uniqueness. So let me say what I mean by that. So what I mean is this. We talked about the fluid state and the solid state as two things that can happen at low temperatures. It is possible that the fluid state can still exist at low temperatures, but it's much less likely than the solid state. So emergence is usually associated with multi-stability. That means that at low temperatures I could have both the fluid state and the solid state, but one of those states is more stable. But as I go to higher temperatures, above say the melting transition, then the only state that is possible is the fluid state. So you have two states possible at low temperatures, but one is much more likely than the other, and one state possible at higher temperatures. So the emergent phenomena is associated with a lack of uniqueness. It's not mandatory that the system needs to be in one state or another. It has several possibilities, and which ones those are is going to be determined by statistical thermodynamics. So that's what I mean by loss of uniqueness. So if you're going to have that, then what that means is you need to have a phase transition that separates states of matter. And so the content of this course will look somewhat like what we do in a phase transitions course, but there's an important difference, which I'll say several times, I expect. And that difference is this. When we're looking at a course on phase transitions, say my course on renormalization group theory, what we're looking at is exactly how the transition occurs. But what we're interested in this course is not what happens at the transition, but what happens above it and what happens well below it. How do you characterize the behavior of matter well below the phase transition case? And we're going to see that as you go below the phase phase transitions, you get new collective properties emerging, the ones that we've started to talk about already, but we haven't discussed all of them yet. So some of the phenomena that we're going to talk about, crystals, magnetization, superconductors, quantum Hall effects, and so on. So those are the typical things in condensed matter physics. Then you might go a little bit further afield and you might say, well, what other kind of emergent states are there? So turbulence, fluid turbulence is one of them. Gravity is probably an emergent phenomenon. There's a whole literature on gravity as a kind of elasticity theory of space-time. And then, of course, life itself is an emergent property and something that is, I'll say something about in either today or next lecture. So really, we have this interesting idea that if we can understand emergence in a meaningful way, we can understand how molecules come to life, how we even get the phenomenon of life in the first place. And I will say something about what I mean by that later. Okay. Any questions before I get into this next bit?
There is one in the chat.
Okay, I can't see the chat because I'm on full screen. Let me have a look and see what the chat question is. So the question is there a specific reason to think there is no ultimate reductionist picture? That's a good question. So I would say, I guess my answer would be partly philosophical and partly practical. So my practical answer to that would be is that here is the history of, if you like, what when I was a student used to be called elementary particle physics. So the history of that is that back in the 19th century, people thought that matter was a continuum, and then people got the idea that atoms existed. So then we had the idea that atoms are the indivisible building blocks of matter. And then that turned out a couple of decades later not to be true. We actually have atoms are made out of other stuff, neutrons and protons, and there's the nucleus and the electrons. So actually, when we said that atoms are the indivisible building blocks of matter, actually scrub that, we can split the atom with the stuff inside them. So no, that's not quite true. We actually have to look at neutrons, protons, and electrons as the basic building blocks of matter. And that was atomic physics. And then as you built up your knowledge of quantum mechanics and the technology, we learned that inside nucleons there are mesons and other elementary particles, and by the 50s and 60s and 70s there was a huge zoo of different sorts of elementary particles, and that list kept on getting longer and longer and longer. So you would think that if you had a fundamental theory of something, that it would have very few adjustable parameters. In the work that I do, when I publish a paper, typically, not always, but typically, you'll be able to make a prediction with either 0 or 1 or maybe 2 adjustable parameters. If you look at the standard model of particle physics, it has, I don't know, I've forgotten the exact number, something like 23 adjustable parameters. You have all the particle masses, you have mixing angles and things like this. So there's a huge number of adjustable parameters. So when we think of, say, the standard model as being a fundamental theory, I think it clearly isn't, because it's clearly just condensed matter physics, but done at higher energy scales and with more adjustable parameters. I'm not saying that that's a bad thing. It just says that as historically, as we kept thinking we could go to small and small scales and find the ultimate reductionist picture of nature, that program has completely failed. In the 1960s and so on, people were trying to build what came to be known as the standard model, the electroweak theory, quantum chromodynamics, and so on and so forth. And the idea, for those of you who know about quantum field theory, you'll know that what one tries to do is one writes down Feynman diagrams that describe how matter interacts, and the upper limits of those integrals are infinity. And when you do these integrals, often you will find that quantities you try to compute become divergent. And so you invent tricks called renormalization to try to get around those things and make your calculations be finite. But the point, the point is that in fact we know that that's really not correct, because the upper limits of those integrals tell you about energy scales that you haven't yet probed and understood the basic physics of. So that's one argument about reductionism. I think that it's historically and there failed. I guess I tend to think there should be a different way of thinking about modeling nature, not in terms of, well, here are the basic particles and then let's put in the interactions. That picture assumes that the interactions are some small perturbation around the idea of an individual particle. And in some situations, you can do that. We'll talk about exactly that in this course, the idea of constructing what are known as quasi-particles, effectively non-interacting particles for systems that are actually interacting. But in most systems, that's not true. There's nothing that says you have to be able to describe a system in terms of individual particle properties. And we'll see that in this course. And so really, once degrees of freedom start interacting strongly enough, you have to question the existence of those degrees of freedom as separate entities, because you can't measure them in isolation because they are strongly interacting. So I think we have the wrong mindset, which perhaps came from the roots in classical mechanics, where you started thinking of non-interacting particles doing orbits and things like this, and you start to build in the interactions in a kind of perturbative way, and it sort of biased the way we think about matter. What we should be doing is thinking about matter with the interactions as being the first thing that comes to mind, and trying to understand that. And in a sense, that's the way we're going to be trying to describe matter in this course. We're going to describe matter from the microscopic level, and go from the microscopic level up to the macroscopic level. And then we're going to ask, how could we have just not done that and just started understanding the nature of matter at the macroscopic level without having to ask about what happens at the lower level? And we'll see that one can construct such models based on symmetries and conservation laws and phenomenology and normalization group inspired thinking. Okay, so that's probably a much longer answer to the question that you asked, but did I go some way towards answering your question? And I don't know if I'm saying your name right. Rajas says thanks. Anybody else want to ask any follow-up to that? Okay, so I want to talk about emergence in its relation to complexity, because that's how I started off. And let me just keep an eye on the time here. So, okay, we're good. So I've drawn here a kind of sort of bird's eye view of science, if you will, which is somewhat idiosyncratic. At some low level of description, you have atomic physics, then you have the atoms interact together to get what we call solid state physics, or more generally, condensed matter physics. Matter can organize into living systems, so I've put here cell biology. Of course, cells interact to form multicellular organisms, or biofilms in the case of bacteria. These living systems are then part of a much bigger system, an ecosystem. They have some kind of community structure. Those ecosystems themselves, which are really defined by the way in which energy flows through the system to the lower level organisms that make up that ecosystem, those can self-organize into social systems and economic systems and so on and so forth. So this is a kind of picture of how you go from very simple physical laws at the atomic scale to systems which are really complex and a complete challenge for us to describe and a complete challenge for us to be able to make predictions about. So I would say that at this level, if you just think about the atoms, emergence sort of starts, if you will, round about here where we're talking about condensed matter physics. And so that's why this course is a sort of standard course in the condensed matter physics sequence here. But some of the concepts equally well apply to these other areas. Okay, I would say complexity, which is harder to define than emergence, starts somewhere here, and I have some kind of way of thinking about what do I mean by complexity, which I will get into a little bit, maybe a little bit later, or you can ask me at the end of the lecture. But what I want to say for now, though, is emergence begins with strongly interacting condensed matter physics. Or does it? Okay, it seems perfectly reasonable, but let's take that little blob there, atomic physics, and let's blow that up. So I've now shifted atomic physics now to the center of the screen. Condensed matter, cell biology, etc., is now pushed off to the right, and then under atomic physics we have nuclear physics, quarks and gluons, strings, whatever you have. And so you can see that even at these levels of description, we have emergent phenomena going on. And so I think it's true to say that you have emergence at every level of description going up to larger scales. And even string theory, which was supposed to be sort of the reductionist theory of everything and so on, we know that string theory is emergent. If you look at string theory and look at the number of ground states of the theory, what you read is that there's something like 10 to the 500 ground states of string theory. So remember we talked earlier about emergence as being associated to multi-stability and multiple states. So you can see that even string theory itself is some kind of effective theory of something more fundamental. And so we don't really have a good way to understand this, the idea of there being anything fundamental. Okay, so let's talk a little bit about misconceptions about emergence. So sometimes if you decide, well, I want to go and read about this, I'll go and look on Wikipedia or search the internet. What you'll find is the idea, particularly I've found this amongst talking to philosophers of science, talking to biologists, social scientists, is that emergence is properties that are surprising and unpredictable. And so the idea is that you would never be able to observe these properties or figure them out by any process of analysis. And so that's a picture of emergence that's sometimes called weak emergence by philosophers of science, and you can't really predict that they'll be there. You just have to go and do the experiment, and I don't believe that that's true at all. I think there's many statistical mechanical techniques to predict emergence in physical and biological systems, and the subjective difficulty of a calculation is not really part of the definition. So, because I work on complex systems and I often get invited to conferences by philosophers of science, which may surprise some of you who know me well. The reason for this is that when I started doing work on the normalization group, that ended up inspiring a whole school, or a really rather wonderful school of philosophy of science, which understood that the way of thinking about scientific reasoning and scientific explanation that we're going to talk about in this course was really different from what people who thought about the process of science had originally came up with, the idea of from Popper and Kuhn and other people who have tried to argue about what is the process of science. So what hadn't occurred to people before was the idea of emergence, the idea of universality, the idea of renormalization group, and the idea of minimal models. And so that was a real challenge to the way that philosophers of science thought about the process of doing science. And so that's why Leo Kadanoff and I were, became involved and asked to participate in discussions about this, about the philosophy of science, if you will. So that's that. Now, what is emergent? I told you what it isn't. Here's an attempt at a definition. It's a non-mandatory property of an entire system due to the interaction and self-organization of its components. So if you wanted a one-sentence description of emergence to put inside a fortune cookie, that might be it. The non-mandatory, by that I mean the loss of uniqueness in large-scale properties as you vary some parameter, such as temperature. And we talked about that when we talked about fluids and solids. And the same thing is true in other systems. So I've given here an example of a magnet at low temperatures. The state with magnetization is found experimentally and in simulation and in theory. The state with no net magnetization at low temperatures is also an allowed solution of the equations, but it's an unstable solution. So there's this multi-stability, the non-mandatory nature of the system. The emergent state exhibits generalized rigidity, which is an outcome of the collective interactions between the components. Okay, so I think this is a good time to end. It's 3:17. We're supposed to end at 3:20. What I'm going to talk about next is the emergence of the emergence of emergence, if you will, the onset of emergence. Talk about scaling, phase transitions, and fluctuations, and what is the difference between what we're doing in this course and what we're going to be doing in a different course that I teach on phase transitions and renormalization group. So let's leave it like that for now. Let me unshare my screen. I'd like to throw it open for questions if there are any.
Professor, could I ask you a question?
Please. Who's speaking?
Yeah. Mark.
Hi, Mark.
Hi. Hi. So I guess I'm kind of building on what you were talking about in terms of reductionism. Is there any sense in which emergence could be viewed as reductionist? And so when you were talking about the idea of scales and how physics can emerge from microscopic laws into macroscopic phenomena, do we see any self-similarity in the way that the physics emerges between different scales, for instance, going from, say, atomic to collective phenomenon in terms of continuous mechanics, as far as like building up from that? Are there similar ways that these things emerge, or is the emergence always different depending on from what scale you go to?
No, I think there's general principles or general common themes in emergence, at least in physical systems. But your question is a very good one, and it's an open question, I would say, because if we know all about emergence in physical systems, then why don't we know anything about emergence in biological systems? So I think the difficulty there is you can't use the same sorts of techniques, although you may have the same sort of perspective. So, and one of those differences is that mostly in this class, we'll be dealing with systems in equilibrium, where things are much easier. When you're dealing with systems out of equilibrium, it's much harder to do it. And of course, living systems and complex systems, which are always living, are out of equilibrium. And so I think it's really that there's very common themes in equilibrium. I mean, when I was a graduate student, there were lots of conferences, entitled Common Themes Between Condensed Matter Physics and High Energy Physics. And then when I became a postdoc, there were common themes between condensed matter physics and cosmology. And that was the time when cosmological phase transitions were discovered and the inflationary universe scenario and things like this. So in these systems, we kind of, they're pretty much common themes, and it's really just a question of, well, the gauge group is much more complicated if you're trying to understand the emergence from in grand unified theories than if you're trying to understand what happens in an XY model magnet or a superfluid. But the basic principles are pretty similar, and how you approach it is the same. When you look at systems of non-equilibrium, like the things that I study in my research, things such as dynamics of phase transitions, fluid turbulence, those are kind of stepping stones between equilibrium, the stuff we're talking about in this class, and the stuff we'd really like to understand, which is living systems. So I think it's a good question, and I think there's, but I do think I would say this though: if you've had the experience of understanding emergence in these simple systems, you know what kind of questions to ask about the more complex systems. So, for example, I'm a condensed matter physicist, so I look at a swarm and a flock, and I ask myself the following question: what holds it together? I think of a flock. So smear out the flock so you can't see the birds, and now you just see this big bubble that's sort of floating around and having these sort of big oscillations like that. And if you just saw a cartoon of that, you'd say, oh, well, that's just a bubble in zero gravity or microgravity in the space station, and it's just flopping around, and what we're seeing are the normal modes and the surface tension and things like that. Well, yes, that's true. Great. So how do I understand those things in a real swarm? And the way you understand those things is kind of reductionist. The mathematical techniques that we would use are reductionist. In fact, I in that particular case, I have an answer to that, which is, if you make a model of self-propelled matter that moves around and looks at its neighbors and sees which direction its neighbor is going in, and it tries to follow that direction. That's a very minimal model of a flock or a swarm. And so you can program that up, and you'll see it'll do swarming. And then as you say, well, what holds it together? What is the analog of the interaction strength between the degrees of freedom? Well, of course, in a living system or a social system or flock, it's basically information flow. So you can say, well, okay, let's suppose that I've got a bunch of birds flying around in a flock, but now let's suppose that the birds can't see very well. Okay, so that I don't get very good information about what direction my neighbor is going in. As I try to lower the information transfer between the birds, say by what they can see, what's going to happen? Well, while this bird has flown off in that direction, I've not noticed that, and I've gone off in that direction, and so the flock will fall apart as a function of varying a parameter which describes the information flow between the active degrees of freedom in this living active system. And so thinking about it in that way, of course, is a very reductionist way of thinking and making a reductionist model. But we're trying to understand what is the simplest model that we can use to then try to understand the macroscopic phenomena that we're trying to understand. Does that answer your question, Mark?
Yeah, definitely. I guess it's kind of like, rather than reductionist, it's almost like inductionist, because it's like if you could understand the relationship between the two phases that you're looking at, then you could sort of consistently build up from there. But I guess there's that difference between equilibrium and non-equilibrium systems that makes it a little bit tricky.
Right. So it is. I think it is interesting that physicists are the most reductionist of scientists in some sense, but in the other sense, at least we recognize that there's two ways to think about things: a sort of bottom-up approach and a top-down approach. And the thing that I want to emphasize, and if you took my stat mech class, you'll remember we started with this in statistical mechanics as well, which is the top-down approach, where you understand what happens as an inevitable consequence of the flow from microscopic to macroscopic, or the normalization as you go up to larger and larger scales and smaller energies. That is a much more powerful approach than just being able to start off with a reductionist picture and then put in the interactions and then hope you can compute stuff. And the reason, as you'll remember from my stat mech class, is that if I'm calculating, say, the properties of a liquid from the properties of atoms bouncing around in a box, I can do that calculation, and I can even derive the Navier-Stokes equations. But that calculation is subject to the limitations of my starting theory. And that starting theory is a calculational scheme that is perturbative in nature. And so I can predict the existence of the Navier-Stokes equations describing fluid flow only within the regime in which perturbation theory is appropriate, which is very dilute gases. Whereas we know that Navier-Stokes equations describe fluids which are incredibly dense, where the atoms are strongly interacting. And so this top-down approach, where you think about the effective theory from the get-go, rather than deriving it microscopically, that's really, in a sense, the main message of this course. Thanks for the question.
Yeah, thank you.
Okay. Anybody else? Any question you want to ask, however it's elementary, don't be hesitant.
If no one else has any other questions, could I ask one more quick question?
Let me just see if anybody else is raising their hand or anything like that on the other screen here.
Actually, I do have one.
Good, go ahead.
I think I haven't done a comprehensive study on both Einstein condensation, so I'm wondering whether there can be some material or resources you can recommend.
I would say go and look at the course notes for my statistical mechanics course. That's probably a place to start.
Okay.
Yeah. So people who are auditing who haven't taken advanced quantum mechanics or stat mech, this course is a so what's the problem called? Cafeteria course, or what is the name what is the name we call these courses that are fulfill a general requirement?
Breadth course, is it?
What's it called?
Breadth course. Yeah.
A what course? I couldn't hear whoever was speaking.
I think it's a breadth course.
Breadth course, that's the word. Okay, there used to be course. Thank you so much. Who was that who was just speaking?
It was Dimitri.
Oh, thanks. Nice to meet you. Okay, yeah, it's a breadth course. So it is a breadth course, but it's not an elementary course. So if you haven't done the prerequisites, you will find it tough going, because we will go fairly fast over some parts of this. So yeah, but anyway, if you want to just message me, email me privately, I can, whoever needs more, needs a refresher, let me know. I can make some suggestions.
To get us excited for the second quantization review homework, could you give us just a overview or sales pitch, if you like, for the power of the second quantization method, which is always something I've struggled to get from just going through the motions of the calculations?
So your question is, why do I need to learn this? What's the payoff?
Yeah, or just, how does it fit into the framework of all the stuff that I know, and what can I use it for?
Right. So ultimately we're going to be studying. So one of the things I want to explain to you in this course is how, if I take an interacting system, how do I describe it in terms of quasi-particles? How do I study the collective behavior? How do I look at the topological structure of the description? And how do I solve the many-body interaction problem? Now, one way to do that is by using full-on quantum field theory and many-body theory, but I want to get to the results much quicker than that. And so we're going to be able to do, you're going to be able to do it as a homework exercise, what Bardeen, Cooper, and Schrieffer got the Nobel Prize for, 50 or 60 or 70 years ago, whatever it was. So we will use quantum field theory, but in a really simple formalism, but I'm going to show it to you in a way that is very powerful. We won't be using perturbation theory, we'll be using a non-perturbative way to do that. So it enables you to do calculations which would be really, really hard if you were just doing them using wave functions. And the reason that I want you to have facility in this right now is because we're not going to be using them for a little bit. But in a while, we will be constructing quasi-particles. We will be looking at the excitation spectrum of systems. We will be looking at systems in much more detail. It's really the foundation of condensed matter physics. So that's really why it's worth doing. Now, there's another payoff. You might say, well, I don't care about that. I'm in this course because really I just want to satisfy the breadth requirement, but really I want to become a biologist. Okay, so in my group we study biological systems, we study ecosystems, we study fluid dynamics, and we actually use second quantization to study those systems. So here's a picture of an ecosystem. Okay, I have a space, and now what I have in it are two kinds of creatures. Wolves and sheep. Okay, so the wolves are the predators and they eat the sheep, and it's a pretty strong interaction. That if I eat you, that's a pretty strong interaction. I think you'd agree, right? So now what you want to know is this: I've got a bunch of these creatures, and some of them are eating each other. The ones who are the prey, they're eating grass. They're all busy making babies, and they're interacting in some way. How do I describe the behavior of that population? And the way you might say, well, it's very easy, right? I just write down a differential equation. I learned about it in my math methods class on my mother's knee. I just simply have to write down the Lotka-Voltaire equations, two ordinary differential equations that describe the population dynamics of the predator, which eats the prey, and I can write down logistic growth, and I can write down differential equations that describe that. So you can do that, and that's what's in Ecology 101. If you do that, though, what you find is that it doesn't work. So let me tell you how it doesn't work. The reason it doesn't work is this. Here's the physics of this. Okay, I've got sheep and I've got wolves. The sheep eat the grass and their population goes up. Wolves come along and they say, oh, there's lots of sheep to eat. So they start eating lots of sheep. And the wolf population goes up because they eat lots of sheep, they get lots of energy, they make lots of baby wolves. But now, of course, they eat so much of the sheep that the sheep population goes down. And once the sheep population goes down, those wolves are now too abundant, and so they starve. So their population goes down. So now there aren't too many wolves around. So now the sheep can start making babies, and their population will go up. And this cycle repeats. And so what you would expect is that the population will actually have a cycle rather than just a constant mean value. If you solve the differential equations that describe that story that I just told you, that bedtime story that I told you about the wolves and the sheep, you can see intuitively it will give you population cycles. But if you write down that in differential equation form and try to solve it, you will find that the dynamics has a fixed point which has no cycles. So then you scratch your head and you say, oh, I know what the problem is. We didn't take into account that there's some extra nonlinearities in the problem. For example, wolves can't eat an infinite number of sheep. They can only eat one or two or something like this. So you put in predator satiation, for example. And you can explain what would be a good way to describe that. And when you put it in, you find it does give you these population cycles. So you think, great, problem solved. Except the problem isn't solved because you think, wait a minute, that doesn't seem right. I could convince myself by purely verbal argument that there should be population cycles, and I never had to invoke the idea that there was population satiation. So why did I need to invoke that in the differential equation description? Okay, so then that's a kind of puzzle. Now you think of this as a physicist. So you say, okay, fine. Let's think of an ecosystem. I have predators and preys. We're going to think of them as just particles bouncing around in a box, and they interact. So what happens when a predator eats a prey? The predator, the wolf, comes along, encounters a sheep, and it eats it. So it reduces the number of sheep by 1. And then it makes a baby, and so it increases the number of wolves by 1. okay? And those are quantized, right? Everything that is quantized is like a photon, a proton, a neutron, a meson, and so on, okay? A person is also quantized, right? There aren't any half people floating around, okay? So these processes of birth and death are integer valued processes. So that means I can say, right, I'll write down a quantum field theory that says I start off with a state, and then I can add a creation operator that will create, or field operator that will create a wolf here, or a field operator that will create a sheep over here. I can write down an interaction between them that will create more predator, more wolves, and diminish the number of sheep, the prey. And so I can describe everything that is going on in that ecosystem in terms of the interaction between these creatures at the individual level by annihilation and creation operators. And the space that I have that describes the system has varying numbers of particles in it. So it's not a Hilbert space, it's a Fock space. So this is a classical system described by annihilation and creation operators that add and subtract particles to the system in units of one. It's not a quantum system, because if I want to know the probability of something, I just have to look at the matrix element of that of the operators in that space. I don't have to take the absolute value of the matrix element squared as you do in quantum mechanics. But other than that, I can now use this quantum mechanical formalism to describe this system. I can write it down in terms of path integrals. And if I ask what is the state of the system, what I discover is that the shock noise that arises from the discreteness of the creation, the birth and death processes, that is what creates the population cycles. So in this description, using annihilation and creation operators, by looking at the individual level rather than this other level, I'm able to get a correct description of the system with only the minimal amount of interactions. And so this is an example there of why knowing annihilation and creation operators and second quantization is useful. It's really not so much to do with quantum mechanics. It's a description of systems which are quantized, and they can be classical or quantum mechanical. Now, it's particularly useful when they're quantum mechanical, because some of the problems we want to solve in condensed matter physics, for example, are quantum mechanical. But it's not restricted to that.
Gotcha. Thank you.
Okay, are you going to do the warm-up sheet then?
With great enthusiasm.
And the nice thing about it is you'll learn some very basic manipulations which you've seen before, and you should be able to breeze through them. Then you'll see some things that you probably haven't seen before, like how you can derive the Bose-Einstein and Fermi-Dirac distributions in like one line of algebra from the properties of annihilation creation operators and commutators. And then you'll see how to make literally a collective state of elastic waves using these things. So there's things in it. I'm saying it's a revision exercise, but in my experience, every student who has taken it in the past has found something in it that they didn't know you could do with annihilation and creation operators.
Thanks.
Okay, thanks for the question. See, I like going off on tangents, but I think that's why you're here. You can get all this, you can get all the regular stuff from the book. So, but you can't get all the other stuff from the book.
Right.
Any other questions?
Yeah, can I ask a logistical question? Is there going to be for the revision worksheet? Is there going to be like a way to check our answers and stuff? If we feel shaky about something, we should just talk to you, and if we feel shaky about one of our answers.
Yeah. So that's a good point. So let me just say something about that. So the first thing is that I don't tell anybody the answers to my homework problems. Okay. So the reason for that is I'll show you. Let's try an experiment. Let's see if this will work. This may not work. So if it doesn't, if it doesn't work, I will. Let me try sharing my iPad. Let's see how well a Blackboard will work. Oh, it's going to work. Okay, you can all see my screen, right? Okay, so let me just show you what happens in my courses. So this is the scores on say homework, and this is the probability density of the score, and this is what happens. Well, this is usually what the distribution of scores looks like. So usually people do pretty well. So it looks something like that. Okay, that's the distribution of scores. So I once did the experiment where I gave out the solutions to my homework, and then I looked at what happened in the following year. I looked at what happened in the following year. So the following year that I did this, my distribution of scores, so there's somewhere here is 100%. Okay, so my distribution of scores the following year was something like this. The delta function. Okay, and one thing about this delta function is kind of amusing, is that delta function was not at 100. Okay, why not? Well, the students who had inherited, shall we say, the solutions from the previous students also got my mistakes as well, and so we got a distribution like that. So I decided that I'm not, I don't really care about scores and so on. My goal is to teach you, and if you're doing this, then if you're doing this, then you're not learning. So I try to I don't give out the solutions. That being said, if there's anything that you don't understand after your homework has been graded, and the way the graders will grade the homework is they'll look through it and they'll see if you got the wrong answer. Oh, this is where you went wrong on this line here. Maybe you should include the conservation of angular momentum or whatever it might be. And then the idea is that you would then go back and look at that and say, oh yes, I should have done that, and then I would have got, then it would have all worked out. So that's how you can do a reality check. And if that doesn't, if you still are stuck, you should talk to the grader and you should talk to me, and we'll try to give you hints, and then eventually help you discover what the right answer will be. So in terms of the second quantization, so we will grade it, and we will look at what you've done and try to give you hints about it, and then you have an opportunity to if you still don't understand from what the grader has written down, ask the grader, ask me, and we'll try to help you with that. Does that sound reasonable? Whoever asked the question.
Yeah, that sounds good. Thanks.
Okay. Okay, so I think we are done. So I'm going to stop the screen share and stop recording.